How can AI be strategically leveraged to tackle productivity challenges in structural engineering? And then how do you identify which real-world AEC problems are best suited for AI solutions?
There are two types of applications. One is where you are trying to get access to the most relevant piece of information for you to do your job in engineering. It could be also searching through your own past historical designs to find something that's closest to what you want to do and then use that in a new design.
Welcome to this episode of the AEC Engineering and Technology Podcast, a podcast dedicated to helping engineering professionals find technology that fits their needs. Did you know structural engineers spend nearly 30% of their time on tasks that can be automated or streamlined? As the demand for smarter, safer, and faster infrastructure accelerates, the real question isn't if artificial intelligence, or AI, will transform structural engineering, but how soon. Joining me today in this episode are Doctors Shirley Dyke, Donald A. and Patricia A. Coates, Professor of Innovation in Mechanical Engineering at Purdue University, and Dr. Vedhus Hoskere, Assistant Professor of Civil and Environmental Engineering at the University of Houston. These two leading researchers are not only advancing AI in structural engineering, but also spearheading the proposed VISER Center, a groundbreaking collaboration connecting academia, industry, and government to solve real-world AEC challenges. We'll explore practical use cases, lessons learned, and how AI can be strategically leveraged to boost productivity and resilience across the AEC industry. I'm your host, Nick Heim, and this is the AEC Engineering and Technology Podcast. With that, let's jump into today's episode. It's now time for our conversation of the week with Shirley Dyke and Vedhus Hoskere. Both of you, thank you so much for taking the time to join the show, and welcome.
Thank you very much for the invitation.
Happy to be here.
Yeah, and this is a really exciting episode for me because once I saw the work that your lab was putting on through a colleague, I was very excited to get to talk to you both and kind of, share the knowledge and let everybody else know what you guys are up to. So we'll just start with a simple one to both of you. Can you tell us a little bit about yourselves? What led you to pursue a career in structural engineering and how your interest evolved into exploring artificial intelligence as a tool for advancing the field?
So I'll get started and Vedhus can fill in his details. So I started originally by wanting to be a veterinarian, but somewhere along the way in high school, I decided that I was more interested in things like vibration and control and decided to pursue a path in engineering. Aerospace engineering and civil engineering are the disciplines that I focused on. And where did AI come in? Well, it's clear that in civil engineering, we can't do a lot of experiments on full-scale buildings. The world is our laboratory. And so by understanding what happens in the real world, we can really determine what the weaknesses are in our structures and how to deal with them. So data being collected every day by engineers around the world is what makes it possible to use these AI methods in a powerful way to improve our structures.
So for me, I come from a long line of structural engineers. My great-grandfather was responsible for the design of some iconic dams in South India. And my grandfather and father are also, they had successful careers as structural engineers. So I was always exposed to structural engineering growing up and something that I always considered. In grad school, I went to the University of Illinois, and during my research there, I was being exposed to advances in deep learning and computer vision in the middle of the 2010s. With all these massive data sets available and access to compute, I was fascinated by the capabilities that these deep learning systems were exhibiting, and became very interested in seeing how those tools could be applied to the problems in structural engineering.
So both of you guys just have this, so traditional engineering background, like we all did, right? My background is civil structural. So we all went through embedded accredited programs and did our graduate work, et cetera. But what's interesting to me is that you guys see this opportunity to use artificial intelligence in a fairly traditional industry. I don't think we're kidding anyone when we say that's just the nature of our business. So it's really exciting for me to hear that there's so much interest in what you guys are doing, and I know we'll get into that in a little more detail as we go through the conversation. But Vedhus, to follow up on some of your points, how can AI be strategically leveraged to tackle productivity challenges in structural engineering? And then how do you identify which real-world AEC problems are best suited for AI solutions?
Yeah, the way I look at it, I think there are two types of applications. One is where you are trying to get access to the most relevant piece of information for you to do your job. And so this could be things like searching through a new building code that you need to be looking through to find something that's useful. It could be for a junior engineer trying to understand what a specific requirement is or some concept in engineering. It could be also searching through your own past historical designs to find something that's closest to what you want to do, and then use that in a new design. And so this type of a retrieval problem, I think, is something that AI can be very suited to, because it can allow you to search through a large set of information and identify some things that are most relevant. The other type of application, I think, are those that help with the core aspect of what we're trying to do as structural engineers. And this can also be broad. For example, it can be related to inspections. It can be related to design. But with modern AI systems, the thing that is different from the previous generation of AI systems is that they have a broad understanding of the world. They are able to make decisions, and they're really good at understanding what is inside pieces of data. So, vision language models are very good at understanding images, and they know so much about the world that it's easy to teach them some specifics also about structural engineering, so they can be leveraged to interpret what's inside an image. Similarly, we can also expand these capabilities to interpret what is inside drawings and other sorts of visual information. For design problems, as engineers, we're making a lot of decisions. And if there are parts of the process where the response of the AI is not going to affect the safety of your final output, then it's okay to use the AI to help come up with suggestions or options that the engineer can then review, applying their full understanding and knowledge about the problem. So even for a design scenario, I think there are going to be opportunities where AI can help come up with different design options that an engineer can then carefully review. And this can help not only increase productivity, but offer new capabilities as engineers explore more of the design space.
It's a really nice summary of Edison. And what I heard was almost like a sliding scale from, well, let's just say maybe how critical a task is, right? Like, so you gave an example of just search and retrieval, right? Like, hey, I know I designed this base plate detail for this client about 3 years ago on this project, and it's a good fit for what you're doing now, and you just can't seem to find it. Well, that's a great application for search. You mentioned young engineers and code interpretation, right? Maybe, helping them break down an empirically derived equation to help them better understand where it's coming from, all the way up through perhaps some assistance with critical design decisions. So I like the way you phrased it, because to me, at least, like, those are some pretty clear examples of how the technology can be used to partner with structural engineers and maybe alleviate some of the fears that our peers have, depending on what their exposure to the technology has been.
Yeah, I agree. And I think you summed it up really, really well there.
And I actually, I love these specific use cases, because I think it gets people's minds churning, and it allows them to just think about how to apply what others are doing to their specific scenario. So that'll lead me to my next dual question for you both. And Shirley, I'd like to start with your input on this one. Can you each share a specific AI-driven structural engineering project you've worked on? And what technical or practical challenges did you face, and how did you overcome them?
Thank you. So one of the projects that we started with in this field was the development of what eventually became ARIO, the Automated Reconnaissance Image Organizer. The world is a great place to understand how our structures perform under real circumstances. And although the data was very prevalent, there was so much of it that people were not using it in the ways that it was intended to be used. So what I mean by that is that engineers would go into the field and collect thousands of photos, and they would come back and use 5. And that's great, but all of those other images also contain information, and that data can be used for many purposes well beyond what it was intended for. So early on, we developed the ability, and this early on means about 2016 or so, we developed the ability to classify those images and organize them so that engineers could go and find what they were looking for quickly. So the Automated Reconnaissance Image Organizer is a tool that embodies that capability. How did we, overcome some of the challenges? Well, although we had 100,000 images, the big challenge is actually getting ground truth. So you have to label all of these data. That takes a tremendous amount of time. So we had teams of students working toward that. But then bias can become an issue because we found architectural features in one part of the world might actually influence the trained models in such a way that they didn't work as well in other places in the world. So it's not only the structural elements that have a role in how the data is actually classified and how the models are trained, but the architectural features can play a significant role. And so if you don't have data from a certain portion of the world, a certain region of the world, then it actually can bias your results. And so these cluttered and unstructured images that are being collected are very different than what is typically applied for classification, where we're looking at dogs and cats and oranges and apples. Those are fairly straightforward problems, but structural engineering is not nearly as straightforward.
That is.
So one project that we're currently working on is developing guidelines for efficiently creating what are digital twins of structures, for example, bridges. The challenge here is to come up with a compact but faithful representation of your infrastructure asset that can be useful for a wide variety of downstream tasks. And so for this to come to fruition, you have to think about what is the decision that you want to make about the asset. For example, for a bridge, you may want to think about, do I need to be making repairs? Is it okay if I allow the bridge to stay as is for an extended period of time? And do I have some data to back up that decision? Right? So if you want to have some evidence to be able to make these decisions more confidently so you can optimally utilize your resources, then you want to have some representation of that asset that you can use for this purpose. So the challenge then is for specific decisions, what is the process that you need to be adopting to collect data from these structures? And then once you collect that data with that specific structure in mind, how do you process all of that data to create this representation and then use it for decision making? So we've been working, both trying to think about this whole problem and also validate the ideas that we've been thinking about in the field by going to bridges, collecting data, and then having this iterative process. AI is plays an important role in many aspects of this. For example, once you collect images, then you can use different AI techniques to process the images into a really nice digital twin. Traditionally, you can use images and you can produce a photogrammetric point cloud, but then that point cloud is not going to be perfect. But you can train AI models to look at the point cloud and identify different bridge elements. And then you can, once you know which bridge elements are there, that gives you semantic information about the bridge, where you can then have another algorithm go in and create the sections and do the extrusion automatically. Now, as Shirley mentioned, a big problem is the ability to train these AI systems because you need data for this purpose. So another thing that we've been really working at over the past 5 years is how do you produce synthetic data? Because in civil engineering, we're designing buildings and bridges, and we have the ability to simulate how these structures respond to different kinds of loading. So we have the ability to produce virtual realizations of these assets, and we can create CAD models and we can take pictures of them. So we've been looking at how do we use this what we call synthetic data to automatically generate ground truth. So we can create hundreds of examples of bridges automatically with the script, and that already knows where all the elements are. And then we can teach the AI system with these examples, and then get it to do well on real data. So that's a problem that we've been working on, and we've been making some progress towards. But we can train many small special purpose models, and we can also leverage the large general purpose models for different aspects of this overall problem.
And that's just one of many problems that I'm sure the relationship that you guys have with industry has identified. And that problem is very interesting to me, right? Because I mean, the industry standard today is, right, if you go out to a bridge to go identify elements, it's paper, pen, pair of calipers, and a tape measure. And we're just going to go start looking up, we're going to start looking up sections. If it's concrete, it's a little bit more challenging. But, the fact that you could go from, images to a photogrammetric point cloud to maybe even a structural analysis model with some oversight is pretty exciting. So, and if you're in the audience listening and don't know what that means necessarily, it's just a faster way to get your job done. But like with everything we're talking about today, human oversight is critical.
Yeah, absolutely. As structural engineers, it's a safety critical job that we're doing, and human oversight is going to continue to be key. But we want to be able to have long-term, broader impacts on the built environment. So for that, structural engineers have to have the capacity to do more. And so that's where I think the productivity that AI brings will contribute towards.
And that's a great segue into our next question for you, Shirley. So then how do you ensure these types of AI applications stay aligned with engineering judgment and safety standards? And what responsibilities do engineers and institutions have in building long-term trust and transparency in these AI systems?
So the most important factor in trying to use these and making sure that they ensure safety and are aligned with engineering judgment is that we need to understand their limitations, right? So if we don't understand the limitations of these particular methods, then we're going to always overuse them in ways that they were not intended to be used or were not capable of being used. So understanding the limitations, rigorous testing to make sure that we can validate their performance, but human oversight is going to be the most important thing. So for a long time, we're still going to be checking and making sure that the results of AI methods actually are producing the results that we expect, the results that make sense to the human engineer. We also need to, keep an eye on other fields, because this field is very rapidly changing. It's not something where we're going to develop a tool and start using it tomorrow, and 2 years from now, it's going to be exactly the same. It's going to change quite rapidly, and we need to leverage what's out there while being sure that we know it's up to the task for these safety critical problems. So there are many other disciplines. We have, both of us are at top universities with big faculties, and we work with people in many different fields, and we understand the state of the art, the state of the field, and where it might be going. And we can see different opportunities to bring that into structural engineering in ways that make sense to structural engineers. Now, you also asked me, what role do engineers have? And for a long time, it's going to be, talking to people about AI, trying to understand what the possibilities are, what the limitations are, and making sure that the tools work for them. Other fields are probably not going to be bringing new ideas into structural engineering unless we have that two-way communication. So making sure that there's a two-way discussion about this, like we're doing today, a two-way discussion about how to make this useful for structural engineers, trying things out, discussing when it does not work or when it does work, and bringing those, making sure everything is transparent.
Which is, just go back to our basic roots, right? Like what did we all learn in structural analysis 1, right? Garbage in, garbage out, whether it's by hand, stiffness methods, a complex computer program, having that end control. And I think AI is a very different tool than what we've, I think, seen over the history of the profession. I don't know that the general principle of how you evaluate it and the skepticism you bring is necessarily all that different, though.
Absolutely. I mean, just like finite elements was introduced, 40 years ago into the discipline, we all need to learn how to integrate this into our practice, into our research, whatever it is. So how can we make the most of it while still keeping an eye on it, still making sure that it's producing the right information, the right outcomes, and we take a look at that with our own eyes and ears, so to speak.
And which leads us to our next question, is something I know you two are very proud of and are currently working on. So Vedhus, this one's for you. Can you share more about the vision behind the proposed VISER Center? So that's VISER, maybe what that acronym stands for, and how this multi-sector collaboration between universities, industries, and government is designed to accelerate practical AI adoption in structural engineering.
Yeah. So the VISER Center stands for Visual Structural Expertise for Resilience. And it's informed by Shirley and my experience in applying AI solutions to visual data, which is very common in structural engineering. Could be images, drawings, models, things of that nature. It is a planning phase IUCRC, which is an industry university cooperative research center. So this is a format that NSF came up with several decades ago, and there have been hundreds of successful centers of this type since then. The way it works is it tries to create this win-win-win collaboration between industry, academia, and the government. And so they all have stakes in advancing the state of the profession, the state of the economy, and producing the talent that can do this. And so that's how these IUCRCs function. Here with the VISER Center, our vision is to empower structural engineers with the latest tools in AI and machine learning that they can apply on their own data. Structural engineers have, over the years, a huge amount of data from their past drawings, from their past work, their past design, and also from their inspection efforts that they have collected. And so some of this, a lot of this is usually unique to the company that they're working at. And so being able to leverage their own tools in a secure and safe manner to achieve some of the outcomes that we've been discussing, such as increasing productivity and increasing their capabilities, is the vision of the center. And to do this, as academics, we are trying to train the next generation of students that can then become leaders in the field and have this broad expertise both in AI and in structural engineering. Through the center, industry members will get to work closely with students, and students will conduct what NSF terms pre-competitive and use-inspired research. So the goal is to conduct research that adds value directly to industry members. And this research will be carried out by students that are going to then become experts in AI, in structural engineering, and then take all of the things that they've learned and transition it to industry as they graduate.
Really, really great summary, Vedhus. And just to expand for the audience who may not know how NSF works and how you guys essentially get funding for these types of projects, could you go into some more detail about, let's say, what's NSF's type of contribution and how does industry help support projects like these?
So the way that the funding works is the National Science Foundation funds all of the management costs. And so the university and the management of the center itself would be funded by the National Science Foundation. The universities provide the researchers in the form of faculty and students from many different disciplines. Whoever is needed to do the particular projects can get involved and write proposals. And the industry supports the funding for those projects. So the students and the faculty that get involved in the research are funded directly from the industry support. There is no overhead on that. The universities waive all of the overhead on those funds so that they're directly supporting the research and not the management, not the organization of meetings and things like that. So overall, it's a win-win-win. It's very low cost, and there's a multiplying effect because industry members, say we have 6 or 10 industries representatives, each of those gets a vote in the projects that get funded, and all of them also get all of the benefits of all of the other projects that get funded in addition to the ones that they might have voted for. So all of them really get access to every one of those projects.
And so Vedhus, and then I'll, as a follow-up question to you, could you just explain how that process might work? So let's say, a listener in the audience says, hey, I'm interested in what VISER is doing. I'd like to explore more about how I can get involved to help essentially improve operations at my firm. What would you tell someone with that level of interest?
So first, they're on the right track there, and they can reach out to either Shirley or me. And what we typically do is set up a short meeting with them to tell them more about the center and the details of how it works. And then what we've been doing is having small planning meetings where, few companies attend and we're looking for companies that have similar interests so that the research ideas that are conducted through the center can bring advantages to all of these companies, and they get a significant leverage on their investment. For example, if there's one idea that 5 or 6 companies are interested in, that idea can be supported by the membership fees from just one of these companies, and so we can fund 5 ideas that are of interest to all of these companies. Through the center, we're also looking to advance the industry as a whole. And so what we're able to do is build consensus amongst like-minded companies on what that future direction needs to be. And in structural engineering, having this consensus is important because if everybody is not adopting some of these ideas, then it's difficult to push the industry forward as a whole. And so if everybody's going off in different directions, then that makes it difficult to move the needle forward. But through the center, we have the opportunity to bring people on board, have these discussions, and identify really what are the aspects of structural engineering that we should be tackling, and coming up with solutions that directly add value to these companies, and also producing the talent that enables that. So all they need to do is just reach out to either Shirley or me, and we can get them into our process.
Well said to the both of you. And what I heard essentially was, it's consensus among peers in the industry, right? No overhead for the specific project just because that's covered by the NSF, and then leverage because if you are, like you said, one of 5 companies with interest in a specific research topic or project, you're able to basically put a multiplier effect on your funding, which is, and I can speak from experience, that's just challenging within a siloed firm. So, it sounds like a great opportunity to me, and I'd encourage anyone that's listening and interested to reach out to Vedhus and Shirley for more information. And then Shirley, we'll turn it back to you for our next question. So how could practicing engineers in the AEC space begin building fluency in AI concepts and tools, even without a background in data science or anything that we've spoken about today?
I don't think people need a background in data science. They just need a willingness to participate in the conversation. So uh, joining in some, maybe presentations that occur at professional workshops or conferences, asking questions, submitting ideas, and discussing those ideas. I think it's not clear to everyone exactly how AI is going to get incorporated and how it might change the profession. But without having the conversation, it's certainly going to get delayed considerably. So bringing the best ideas together, having the conversation, and vetting those ideas, and then trying things, asking questions. What we've found over the years is that we get our best ideas by talking with engineers in the practice they have problems that need to get solved. And by talking with them, we can see solutions maybe they can't, because we have a little more awareness of the technology, but we certainly don't have an awareness of what the problems are. So we have to come together. So,
which is great that you guys were able to take the time today, because that's what this podcast is all about, right? It's connecting
Yep.
people and ideas for really just for a better future for the industry. So Shirley, thank you for that excellent summary. And Vedhus, this will be our last question for the interview today, and we'll close it out here. What final piece of advice do you recommend to AEC professionals who want to stay relevant and lead effectively in this AI-driven shift in structural engineering?
It's a really great question. I think as engineers, you are when you're working, you're busy with the deliverables that you need to be rendering, and of course you have specific tasks that you're doing. But I think these days AI tools are really pervasive, and they impacting many things that most people do, right? Generative models, they produce text that can be useful in many scenarios, and they have more and more capabilities that are emerging. As engineers, as Shirley mentioned, they're in a really good position to understand what are the pain points that they are facing. If they also start gaining exposure to these AI tools by using them, which I'm sure many engineers are already, then they can also get a sense of what might be possible. And I think just there, thinking about what might be possible will be a big catalyst in pushing the industry forward and making these things a reality. And so I would encourage them to use these tools and test them and explore, have this experimental mindset where they can. These are general purpose tools that are available, and without naming names, I think people know what these tools are. But I think using them, testing them, makes them understand what these things might be capable of, and I think that's a good education for the nature of things to come, and also will I think motivate them to try to get involved in making that transformation happen.
Which is great, because what we see today is, like, let's just say, playing around with an LLM or any of these tools that are available. It is play in that sense, but it also prepares you to become better acquainted with these tools for, when the day comes, right? And let's say there's a product that's spun out of VISER that catches fire, right? Like, and an engineer is already familiar with, the models behind the technology and how it's used. It's really preparing yourself for what's to come, even if you may just think it's, like messing around. Like today, I fed a large language model some information about a core we took of a precast slab with a topping, and I just said, hey, I just want you to draw me a cross section of it. I mean, it got 70% of the way there, right? One day that'll be like 98, 99%. I'm confident with it. And when it comes, right, now I understand, how to better prompt, what to ask it, how to correct things, just as an example to the audience of what's out there. So I love where you're going with this, guys, because it's, I think, definitely benefit to practicing engineers.
Yeah, that's a really good example.
So Shirley, Vedhus, again, thank you so much for taking the time to join today. As we discussed, right, it is thesis defense season, soon to be final season. So I know you guys are very busy at work, but if our listeners do want to connect with you, right, ask more questions, perhaps, maybe get some specifics on funding VISER, what is the best way for them to reach you?
So one of the ways is to search for us in LinkedIn. We're VISER, VISER. And another way is to reach out to myself, Shirley Dyke at Purdue University. Just search for that. I'm sure you'll find it. Or to reach out to Vedhus Hoskere at University of Houston. Email us. That's a great way. Or reach us through LinkedIn.
Excellent. And Shirley and Vedhus, thank you so much again for taking the time.
Thank you very much.
Thank you.
Please remember, you can find the show notes for this episode at aectechpodcast.com. There, you will find a summary of key points discussed in today's episode, as well as links to any of the resources, websites, or books mentioned during this episode. Until next time, I wish you the best in all of your engineering and technology endeavors. Thank you.